Hey guys, so today I'm going to talk about analysis of variance. I'm also going to record the relationship tests lecture. Alright, so here in chapter 10, I didn't go over ANOVAs yet, so let's do that. We have the analysis, okay, so ANOVA stands for analysis of variance. And it tests the difference between more than two levels or categories or groups on any kind of interval or ratio level DV. So an example of that might be, are dachshunds cuter than other types of dogs? And I say yes, because I have a dachshund. He's cute as hell. All right. Then what we're doing in the formula for the ANOVA is we are comparing between group variance to the within group variance. Well, what the hell does that mean? Well, the between group variance is how much difference there is in the cuteness, for example, of the different categories of dogs. So we look at the difference between each of the categories. The within group variance looks at how much cuteness range there is within each category. So that's what the formula is doing. It's just comparing the between group variance to the within group variance to see if there is a significant difference between the categories, okay? So when we do analyses using ANOVAs, we have to often do post hoc comparisons to actually find out the answers to our hypotheses. So for example, say we were wanting to look at whether blondes will be rated more attractive than other hair colors like brunette or redhead. So we are going to hypothesize that blondes are rated as more attractive, but when we run the ANOVA, we really only find out whether there is a difference between the categories of hair color, right? We don't know which category had the highest ratings. So what we have to do is we have to go look at the means for each of those categories, and we can tell from the mean whether or not blondes have the higher mean, meaning they would be the one that is different, the category that is different from the other categories. So that is a very easy post hoc comparison, but we also have other post hoc comparisons that I'll talk about when we have more complex ANOVAs, okay? So a one-way ANOVA is just going to be testing the difference between one IV that has more than two levels on an interval or ratio DV. All right, so an example might be the average temperature in Kansas will be colder than the average temperature in Arizona and New Mexico. That's easy to see from the mean temperatures in each of those places. You can see that Kansas is different. Is it significantly different? We don't really know, not until we run the ANOVA. All right. So here's some examples. So a two-way ANOVA tests the difference between two IVs, one of those with only two levels. So you can have one IV with two levels and then one IV with more than two levels. All right. And these get kind of confusing because we have because we have two IVs, we have not only our main effects, but we also have the possibility of an interaction effect. So if you look at the pictures here, you're seeing the main effects on the left side. The orange boxes are showing the main effects. So if you see setting, right, the outside setting has a mean across times of 5. And then the inside setting has a mean across times of 7. So we could test the difference of setting outside and inside using that ANOVA, the two-way ANOVA, and see if that 5 and 7 are significantly different. For the main effect of time, which is the 1 hour is 6, 4 hours is also 6, we don't really need to run the ANOVA. Of course, the ANOVA probably would give us those results, but we know, right, that there's no difference if they are the same number. All right. For the interaction effects, we're looking inside at the green boxes. what we want to know is, does setting change the outcome based on time? Or does time change the outcome of setting? Does time change the outcome based on setting? So let's think about what this means with relevant examples, right? So let's say you are studying and you want to know whether studying outside is better than studying inside, and how much time you're studying, whether 1 hour works or whether 4 hours will work. So we look at the differences between these, and you can see in the graphs below the table that we have a higher score on, let's say, the test when we're outside for 1 hour than we have when we're inside for 1 hour. Okay? Then we have a lower score on the test if we are outside for 4 hours, or we have a higher score on the test if we are inside for 4 hours. So we can see from the graph and from the table that it's more beneficial to study outside for 1 hour or inside for 4 hours. That's the interaction effect, is taking into account both variables, right? The main effects only take into account one variable at a time. We look at the difference between the two levels on setting, the difference between the two levels on time. But the interaction effect takes both variables into account. Here is another 2 a.m. This is just looking at a two-way ANOVA with a variable that has 2 levels and another variable with 3 levels. So it becomes a little bit more complex, but not really, right? We're still looking at the main effects and the interaction effects. And you can see the graphs there. They show both the main effect. Well, we see that there's no main effects, right? Because it's 6 and 6 for treatment, and across the board 6 for setting. So there's no main effects. Setting alone doesn't influence something, and treatment alone doesn't influence something. But we do have interaction effects, right? So we see from the graph below the table on the left that we have an interaction between setting and treatment that basically shows that doing a psych treatment outside, I don't know, is best, or doing the behavioral modification inside is best, right? Good deal. We can also look at the interaction among the 2 treatments. So these are 2 of the same kind of results. It's just graphed in different ways, showing the focus on either setting or treatment, but it's the same interaction result. Lastly, we have the factorial ANOVA. And the factorial ANOVA is just like a two-way ANOVA, but it allows us to test 2 IVs with more than 2 levels. So if you have 2 variables and both of them have more than 2 levels in them, we can use the factorial ANOVA. An example might be people who are single will differ in their sex expectations from those that are married or dating based on their age group. See, we have 3 levels for each of those variables. Here you can see an example of the factorial ANOVA. The table just gets bigger. We have now 9 squares within the table, but this table just shows, right? The main effect of difficulty shows that the hardest test is the hardest, right? And then the main effect of anxiety shows that when there is moderate anxiety, people do best. When we look at the interaction effects, we can see that from the little figure to the left, that actually low anxiety and high anxiety, the lowest scores occur when the test is hard. You see how that works out? So if the test is hard, you're going to have problems with scores among the people who have low or high anxiety. They both scored about the same. We can see from the table that they scored 35, whereas those with moderate anxiety scored 80. So when the test is hard, we have to take that into consideration, whether or not anxiety is going to play a role. All right. Oh, I guess that wasn't the last one. Here we go. Repeated measures ANOVA is the same as a regular ANOVA, like a one-way or two-way, but we use repeated measurements, which means that we are looking at people's reports, the same reports to the same questions multiple times. So it's a lot like the paired simples t-test, but generally for the repeated measures ANOVA, we are going to have more than 2 measurements, 2 conditions. We're going to have 3 or more conditions that we are testing the difference between. Here is an example that shows how the repeated measures ANOVA works. Here in hypothesis 1, we have blood pressure at time 3 will be lower than at time 1 or time 2. And you can see from the figure there that we are testing the same individuals over time, and we're just changing time, right? So we have time point 1, then we have maybe 6 months later, a week later, who knows, time 2, and then time 3. And we are just looking to see whether their blood pressure is lowest at time 3. Hypothesis 2 is looking at 2 different variables. This is like a 2-way repeated measures ANOVA. So you're looking at blood pressure and different conditions for diet. All right, so here we can see that we're comparing the same people over the 3 time points, but we are going to have different diet conditions and different blood pressure. Okay, no, never mind. Let's start over. All right, so for the repeated measures ANOVA, you can see here just how it looks. We can look at time periods, we can look at conditions. These are 2 different hypotheses, both looking at stuff that would basically be considered a one-way ANOVA, but because we're testing the same people and their measurements being the same on the same variable, we're just testing them over time or testing them over different conditions. Okay, so the last thing I wanted to talk about is how we report effect size for ANOVAs. Effect size, as we've already discussed, talks about the magnitude of an effect. So it's like how big or how strong is an effect. Here we have an example hypothesis. Freshmen will rate COM 228 as more difficult than sophomores, juniors, and seniors. COM 228 is what we used to call this class in at Arizona, so I just didn't change that. But here you see the report of the F test, right? The P is less than 0.05, so we would say it is significant. But then we have that eta squared report, and that eta squared tells us that our effect is pretty large, right? That most freshmen would definitely rate COM 228 as more difficult than sophomores, juniors, and seniors. All right. Thank you. I'm done with ANOVAs.